EP 120, Chapter 18, Topics, Electrolyte Balance and Chemical Buffer Systems. So electrolytes are things that dissolve in water and produce ions. And again, it is important that the amount of electrolytes we gain in the food and liquids we consume equals the amount lost in things like urine, sweat, and feces. So common electrolyte intakes. Common electrolytes: sodium, potassium, calcium, magnesium, chloride, sulfate, phosphate, bicarbonate, and hydrogen ions, all things that we've heard of before. And of course, electrolytes are primarily brought in via food or drink, although sometimes they are produced as a byproduct of metabolism. So regulation intake is obviously based on what we consume. Sometimes we consume things in excess because, well, for instance, salt tastes good. It is thought that cravings that people have might be a sign of low levels of a particular electrolyte, although that is not always the case. And then output, as I mentioned, sweating, feces, and urine. And we control easiest the electrolytes lost via urine. In general, blood concentrations of sodium, potassium, and calcium are tightly regulated. They are very important that those amounts in our extracellular compartments are well regulated. For instance, sodium ions are about 90% of the positive charged ions in extracellular fluids. So we want a lot of sodium in our extracellular fluids, so we want to conserve that, while we don't want very much calcium or potassium. So one hormone that does this is aldosterone. Aldosterone increases sodium levels in blood by saving it from urine. So we end up pulling sodium ions out of the filtrate that will become urine. As a consequence, water is also reabsorbed. Water is also returned to the bloodstream. So we're saving sodium and, as a consequence, also saving water, returning those things to the bloodstream, getting more concentrated urine. Also, aldosterone increases the excretion of potassium. So there's going to be more potassium in the urine. Potassium is going to leave the bloodstream and enter the filtrate that will become urine. So aldosterone, an important hormone for helping to make sure we have high levels of sodium and low levels of potassium in our extracellular fluids. So potassium ion concentration increases. Adrenal cortex detects this and secretes aldosterone. This leads to renal tubules in the kidneys, increasing reabsorption of sodium ions. So sodium ions are being returned to the bloodstream, and increasing secretion of potassium ions. Potassium ions are leaving the bloodstream. And so sodium ions are conserved, potassium ions are excreted. Of course, also very important is the pH of blood. So we need to be able to regulate acids and bases, and specifically the amount of hydrogen ions found in our various fluids. Because acids release hydrogen ions, bases can combine with them, and our body tends to produce more acids. So it's critical to control these to have the proper pH to maintain our homeostasis. So sources of hydrogen ions, mostly byproducts of metabolism from aerobic and anaerobic respiration, aka the making of ATP. Also incomplete oxidation of fatty acids. So again, aerobic respiration of glucose gives us carbonic acid. Anaerobic respiration gives us lactic acid. Incomplete oxidation gives us acidic ketone bodies. So our internal pH is going up because of all the hydrogen ions. And then we also have oxidation of amino acids that contain sulfur, so sulfuric acid, breakdown of phosphoproteins and nucleic acids, giving us phosphoric acid. So we are having a high concentration of hydrogen ions being produced in cells by these processes, and they of course then go directly into the bloodstream. So again, our body has a tendency to make our blood acidic, high concentration of hydrogen ions. Now, some acids are strong acids, and they will iodize completely. They'll break up completely to give you a full amount of hydrogen ions. Others are weak acids, so they only partly ionize, partly lose their hydrogen ions. And then, of course, the bases release things that bind to hydrogen ions. And you can also have strong bases and weak bases. As a consequence, we can use what are known as chemical buffers to help resist the change in pH in our bloodstream. So without a buffer, you start adding a strong acid to that solution, and you will get a dramatic drop in pH. Boom, because there's nothing to resist that change. But if you have buffers, then you can add a strong acid, and there is a resisting in that change. The pH change will be somewhat less significant initially. Eventually, it will overwhelm the system, but at least initially, the system is able to resist the pH change. And this also works in response to strong bases. So no matter whether it's a base or acid being added, the buffer system can help resist pH change. And the ways we do this include via the respiratory system, regulating the pH of the blood, as well as the kidneys helping to regulate the pH blood, as well as the buffers already in the blood that are resisting the pH change, waiting for these physiological systems to readjust the bloodstream. So, buffer systems in the blood. We have bicarbonate buffer system, extremely fast. We have a certain amount of carbonic acid and bicarbonate caused by concentration of carbon dioxide in the bloodstream, and they are always present in the blood. The relative amounts are influenced by breathing, whether you're breathing fast or slow, and because they're present in the blood, they can resist pH change in the blood. We have phosphor buffer system, also fast. This, in this case, is found in the nephrons, going between two different states of phosphate. And again, they can help to resist pH changes in the kidneys. And then plasma proteins in the blood. Again, in the blood all the time, so they're always present. And because one end of the protein has an amine group, the other carboxyl group, they are able to help in the resisting of pH changes. So these chemical buffer systems act extremely quickly so that we don't have a dramatic change in our blood composition if, say, you decide to drink some vinegar. So again, this just summarizes how they function, and good to read over. All right, another way that we can control the pH in blood is by breathing. The excretion of carbon dioxide will alter the composition of the blood and the pH of the blood. So this is somewhat fast, not as fast as the chemical buffers already present, but it allows for a relatively quick response. So examples, you're exercising, increasing cellular metabolism, which means more carbon dioxide is going into the blood, making the blood more acidic. In response, the respiratory centers in the brain say, hey, we need to breathe faster and deeper. And by doing that, you excrete more carbon dioxide, which counters the acidic increase from the metabolic activity in your cells. So again, the reason why we breathe fast when we exercise is because of carbon dioxide, and to get rid of excess carbon dioxide so our blood does not become acidic. So cells produce lots of carbon dioxide. They react with water to produce carbonic acid, which can also become bicarbonate acid, end up releasing lots of hydrogen ions. The brain says, uh-oh, we need to deal with this. So the respiratory center stimulates breathing so that we get rid of more carbon dioxide. So more carbon dioxide comes in from the cells, more carbon dioxide leaves from the lungs from breathing. All right, we can also have the kidneys regulating the pH, the hydrogen levels, by removing hydrogen ions from the bloodstream, placing them into the urine. This is a slower process. Urine formation is slower than breathing. So the nephrons are able to secrete excess hydrogen ions. This would make the blood more basic, so raise the pH of blood and then our urine would be slightly more acidic. So these systems are there to help maintain the proper pH in the blood, which then maintains the proper pH in our other fluids, such as lymph and cerebrospinal fluid, and so on. First thing that happens is, of course, the chemical buffers, first line of defense, resisting the change in pH of the blood. Then we have the physiological buffer sisters come in to readjust things to the ideal levels from increase or decrease in breathing rates and in the removal of hydrogen ions via urine production. So these are secondary defenses, a little slower, but there to reestablish our ideal homeostatic levels. So again, our first line of defense, the chemical buffers already in blood, ready to respond to changes in pH. Second line of defenses requires us to physiologically change what we're doing, either the rate of breathing or the amount of hydrogen ions excreted in urine. That's it for this part.